My name is Seth Kinoshita, and this is Lab 5 of Physics 2211, Freestyle. In this lab, we will explore Newton's second law and the momentum principle, discussing how it applies to the lab. Then, after initial conditions are established, we will discuss how data was collected for using each of the experimental and computational models. Then, we will look at the results and compare the models before the ending with conclusions and what-ifs. The purpose of this experiment was to observe the motion of an object and generate a position versus time graph comparing a computational and experimental model of a falling slinky. The goal was to model the effects of gravity and drag on a falling object's motion. A key concept in this lab is Newton's second law, usually written as F is equal to ma, but as seen in some of our previous labs, it can be rewritten in terms of momentum, seen in the equation below. In this experiment, we are assuming mass is constant and the initial velocity is zero, but unlike previous labs, the net force is not assumed to be zero. Rather, an object dropped from rest will have two forces acting on it as it travels towards the ground. These two forces are the drag force and the weight force. The drag force is a frictional force, which means it acts opposite to the direction of motion. The formula is seen below, with B being the proportionality constant, V being the object's velocity, and J hat being a unit vector in the y direction. Based on this formula, the drag force is directly proportional to the velocity squared, so as an object gets faster, the drag force should also get larger. The other force is the weight force, or the force of gravity. The formula is simply the mass of the object multiplied by the gravitational constant g, with j hat as the unit vector in the y direction. In free fall, when these two forces become equal in opposite direction, the object has reached something called terminal velocity, meaning it will not get any faster than its current speed. The procedure of this experiment was to record a video, or analyze the one on YouTube, of a slinky being dropped from rest. Then we analyzed the video using Tracker and extrapolated the data. Then we manipulated the starter code in GlowScript to create a computational model that models gravity and drag forces applied to the slinky. Then a position versus time graph was created to compare the models to look at differences, and finally conclusions were drawn. The initial velocity was zero because it started at rest, and the initial position was determined based off the axes placed in Tracker shown to the right. Motion is in the negative y direction, and the system was determined to be the slinky, while the surrounding was the earth and the air. When analyzing Tracker, I obtained a graph of data that looks something like this, and this is a preview of the results because it shows the experimental data in the y direction that will be compared against the computational model. So the initial conditions in the computational model were with the estimated mass of the slinky to be around 0.218 kilograms. The initial velocity and position are shown. The time step was determined to be 0.036 because of the frame rate of the video, and the proportionality constant B was experimentally determined through guessing and checking to see which data matched to the closest. So the computational model here, there are a couple key things. The first part is when time is less than 1 second, which is when the slinky has been dropped but the bottom of the slinky has not moved. There are position and velocity update formulas, but the position should not change over this time interval, and this is modeled with the net force being equal to 0 in this portion. Then, between 1 and 2 seconds, the bottom of the slinky moves and the drag force is no longer equal to the force of gravity. Therefore, the position of the bottom of the slinky will change until the 2-second mark is reached. The same position and velocity update formulas were applied during both time periods. After the data was collected from both computational models, a comparison graph was made between the experimental data and the computational model. Overall, most of the data is similar towards the start, but the computational model differs a little bit. The fact that they match pretty well, though, indicates that drag and gravity both played a factor in the real motion of the slinky. Some outliers in this experimental data can likely be chalked up to manual tracking in the Tracker software and variable frame rates from the recording camera. Additionally, the computational model likely overcompensates a bit for the forces compared to real life. On to some conclusion questions. So what if the slinky was thrown downwards instead of dropped? So the initial velocity shouldn't actually matter for this situation. While the whole process would happen in a faster interval, the bottom of the slinky should still remain stationary and the motion should be modeled in the same way. This relates to the concept of terminal velocity being the same even with an initial thrown velocity. The second question is, what if the slinky was held in an outstretched horizontal position at some distance above the ground? What happens to the center of mass? So, because the force is evenly distributed throughout the slinky, releasing both ends simultaneously should exert a net force of 0 on the center of mass. Therefore, the only forces acting on the center of mass is the force of gravity, which changes its kinetic energy. And this means that you can model this specific situation as a point particle system and determine its final velocity of the center of mass right before it hits the ground. It's kind of crazy how all the physics concepts relate to each other, and that's Freestyle.